All right, frequency modulation, demodulation. Frequency modulation, demodulation, intelligence to be recovered the amplitude variations in the variation, the instantaneous frequency of the carrier that either above or below the circuit center frequency. The detecting device must be constructed with the output amplitude very linear according to the instantaneous frequency incoming signals of the type of the frequency modulation have been developed in or used in section mode. With type of the three most common: the phase shift detector, the ratio detector, and the gate beam detector. The slope detection. The able to understand the principle of operation of the frequency modulation detector. You need the first of the simplest form of the frequency modulation detector. Slope detector is an essential tank circuit with attuned to the function frequency either slightly above or below the frequency modulation carrier the frequency. The view A, the figure 3 9 the plot voltage various frequency of the tank circuit, the resonant the frequency of the tank circuit, the frequency at point 4, the component select with the resonant frequency the higher the frequency of the frequency modulator carrier signal at point 2, the either frequency deviation frequency modulation signal fall to the lower point, lower slope of the band pace curve of the bigger points 1 and 3 with the frequency modulator signals applied with the tank circuit view B, the output amplitude of the signal vary with the frequency swings closer to the further the resonant frequency of the tank. The frequency variation will still be present in the waveform and will also develop amplitude variation shown in view B because of the resonance tank of the circuit that varies the input frequency. The signals applied with the diode detector view C. Detected waveform and the output of the circuit have the major disadvantage of the amplitude variation of the radio frequency waveform will pair for the tank circuit to be detected. This disadvantage can be eliminated by placing a limiter circuit before the tank input of the limiter circuits were discussed in each module 9 introduction wave generation. Wave shaping circuit. The circuit is basically the same as the amplitude modulation detector with a tank tuned higher lower frequency from the radio C receiver. Voltage carrier 1, 2, 3, 4 frequencies. Tank circuit. Your diode detector, capacitor, resistor. Foster C-light discriminator. The Foster C-light discriminator, often known as the phase shift discriminator, uses the double tuned radio frequency transformer to convert the radio frequency variations receive the frequency modulation signal amplitude variation rectified filter to provide the output DC output voltage. The voltage vary with the both amplitude, the polarity of the input signal vary with the frequency of the type. The pull discriminator for the curve of the shown figure 310 output voltage 0 when the input frequency equal to the carrier frequency. The input frequency rises above the center frequency. Output increase with the positive direction. Input frequency to the opposite below the center of the frequency. The output increase with the negative direction. Decreased frequency to the left is and increased frequency. Output of the Foster C-late discriminator is affected not only by the input frequency but also to a certain extent by the input amplitude with the limiter state with the detector is necessary. Circuit operation of the Foster C-late discriminator. Figure 311 that shows the typical Foster C-late discriminator collector circuit of the power signator amplifier circuit. The limiter amplifier circuit is a special amplifier circuit that leaves the amplitude of the signal limiting keeping the interference noise level of removing except for the amplitude variation signal of the collector circuit the collector circuit tanks consist of the capacitor 1, inductor 2, capacitor 2, the inductor 2 from the second stereo tune. Both tanks are used to tune the center frequency and come in the frequency modulator signal. The choke L3 is the DC return path of the diode conductor on diode 1 and 2. The resistor 1 and 2 are not always necessary, but usually used when back. The reverse bias resistance of the two diodes is different. Resistor 3 and 4 are load resistors and bypass capacitor 3 and 4 remove the radio frequencies. Capacitor 5 is the output coupling capacitor. The it shows your operation above resonancy, above operation resonance, operation below resonancy. Basically, it's a split phase. Alright, circuit operation resonance. The operation Foster C-late discriminator can be explained with the vector diagram view B, figure 311 of view B, with the show of the phase, the relation between the voltage of the current and the circuit. Let's look at the phase relation with the input frequency equal to the center frequency of the resonant tank circuit. Input signal applied with the primary tank circuit is shown with the vector the E with the primary tank circuit with a simple coupling circuit with the capacitor A with the negligible reaction with the input frequency the radio frequency choke with the L3 with effectively in parallel the primary tank circuit. Although the inductor 3 is effectively in parallel the primary tank circuit, input voltage of the primary tank circuit that appears with the inductor cross with the inductor 3. The voltage of the primary inductor circuit applied with the primary of the transformer 1 voltage reduced on secondary, which covers the current flow with the secondary tank circuit with the input frequency is equal to the center of the frequency of the tank's resonancy with the active resistive current voltage of the intake of the resistance circuit is shown as in the primary tank first circuit. The current flowing with the tank circuit covers the voltage drop across each half of the balanced secondary winding of transformer 1. The voltage drop with equal amplitude with the opposite polarity respecting the center tap of the winding. Because of the winding is inducted with the voltage across the 90 degrees out of favor of the current through with because of the center tap of the arrangement. The voltage at each end of the secondary of the transformer 180 degrees off phase. Voltage 1 and voltage 2 on the vector diagram. Voltage applied by the anode of the conductor diode 1 vector sum of the voltage. Voltage primary tank circle with the voltage 1 showing voltage 3 on the diagram. Likewise, voltage applied by the anode with the diode 2 vector sum of the voltage primary voltage 2 with the shown voltage 4 on the diagram. Resonance the voltage 3 and voltage 3 are equal as shown with the vector same length with the equal anode voltage of the diode 1 and 2 produce the equal currents of the equal load resistors. The equal opposite voltage will develop resistor 3 and 4. Output is taken the resistor 3 and 4 will be at zero resonance since the voltages are equal and positive polarity. So the diodes conduct on opposite half cycle with the input waveform produce the series of the DC pole with the radio frequency ripple to filter it out with the capacitor 3 and 4. Operation above resonance. Phase shift the curve with the input frequency with the center frequency applied with the discriminator circuit with the current with the voltage favor the relationship of the chain with the series tune circuit operated with the frequency will resonate the inductive reactance for the coil increase the capacity reactive the capacitor true is above resonance the tank circuit is acts like an inductor secondary current like with the primary tank of the primary voltage. Now the secondary voltage the voltage 1 and voltage 2 are 180 degrees out with the current with the current with that produced the chain with the lagging secondary current rotate the vector of the clockwise direction. This is called the voltage 1 to become the more phase of the voltage primary circuit, and voltage 2 with it shifted further with the out of phase of the voltage primary tank circuit the vector sum of the voltage primary tank and the voltage 2 is left in the primary voltage of the primary and the voltage 1 above the center frequency of the diode conductor diode CR1 when it's conducted more than diode 2 CR2 because of the heavy conduction the voltage developed across the resistor 3 greater than the voltage developed across the resistor 4 of the output voltage is positive. The operation below the resonance when the frequency input the frequency is lower than the center frequency the current voltage favor the relationship between the tune circuit is operated with frequency lower than the resonance of the capacitive reactance and curve the inductive reactance to curve the below the resonance of the tank that acts like a capacitor secondary current these primary tank voltage the change of leading secondary current will rotate the vector in the counterclockwise direction from the vector to diagram, so you should see that the voltage 2 is brought nearly to the phase of the voltage of the primary tank circuit that voltage 1 shifted further out with the voltage phase of the primary tank circuit with the vector. Some of the voltage primary tank of the voltage 2 is larger than the voltage primary tank of the voltage 1. Diode conductor 1 conducts diode 2 conducts more than conductor 1. Diode 2. Diode 2 conducts more than diode 1 below the center frequency of the voltage develop. The voltage drop across resistor 4 larger than the voltage across the resistor 3. Output across the both is negative. Disadvantage: these voltage outputs can be plotted and shown with the representative of the curve that discriminated discussed earlier in 310. The weak of the amplitude modulation signals a small amplitude reach for the curve the circuit and limiting that level of passing through the limiter shade that can be appeared to the output. Unwanted amplitude variations that cause the primary voltage to fluctuate with the modulation to introduce the similar voltage of the secondary transformer. The diodes are connected with the half-wave rectifiers. These small amplitude modulation signals will be detected. They will be the diode detector will appear on output. This unwanted amplitude modulation interference cancel out with the radio detector to be studied in the next chapter is the main disadvantage of the Foster-Seeley circuit. Alright, your ratio detector. The ratio detector is the double tune transformer to convert the instantaneous frequency variation of the frequency modulation input signal to instantaneous amplitude variation of rectifier provided the DC output voltage varies the amplitude polarity of the input signal. The frequency detector demodulate the frequency modulation and suppress the amplitude noise without need for the limiter stages. Circuit operation. The figure 312 shows the typical ratio detector input tank capacitor primary with the transformer 1 inductor 1 2 center frequency with the frequency management frequency modulating signal the demodulator the secondary with the 1 the transformer the inductor 2 capacitor 2 also with the tank circuit the center frequency essentially a third winding of the inductor may provide the additional inductive coupling with a reduce the loading effect of the secondary primary circuit. The diodes 1 and 2 rectify the signal with the secondary tank capacitor 5 and resistor 1 and 2 operating level of the detector capacitor 3 and 4 determine the amplitude the polarity of the output resistor 3 limits of the peak of the diode current furnace of the DC return pack rectify signal the output of the detector is taken from the common connection between capacitor 3 and 4 the resistor load of the resistor 5 and the resistor load is the load resistor RL is the resistor load resistor the resistor 5 and capacitor 6 and 7 the low pass filter to output. Figure 312 show the output detector. Your circuit operates with the same principle of phase shifting as the Foster-Seeley discriminator within the discussion vector diagram. You illustrate the voltage amplitude polarity with the condition of the resonance above the resonance below resonance. The same vector diagram applied with the ratio detector will not be discussed here. Instead, you will be studying resulting current flows with the polarity simplified schematic diagrams and detector circuits. Operation at residency input with the voltage primary with the tanking is applied with the primary figure to the 312 with the plate for the inductor 3 with the inductive coupling effectively connected to the parallel primary tank circuit. At the same time, the voltage is induced to the selecting secondary winding caused the current flow above the secondary tank circuit. A resistant tank that acts as a resistive circuit that is tank current with the phase of the primary voltage of the current flowing through the tank circuit causes the voltage 1 and 2 to be developed in secondary winding transformer 1. The voltage is equal and with magnitude the operating opposite polarity with respect with the center tap of the winding. The winding is inductive with the voltage dropped across 90 degrees of the phase of the circuit through it. Figure 313 for the simplified schematic diagram ratio of the detector resonance of the voltage applied with the cathode. The diode 1 is the vector sum of the voltage 1 and voltage primary tank circuit. Likewise, the voltage applied with the anode. Diode 2 is vector sum of the voltage 2 and the voltage primary. Tank circuit with no phase shift occurs. The resonance both voltages are equal. Both diodes conduct equally. Each equal current flows cause the same voltage drop. The cause resistor 1, resistor 2, capacitor 3, 4, which are the equal voltage opposite polarities. Let's assume that the voltage capacitor 3 and 4 are equal in amplitude. 5 volts opposite polarity. Total charge across the capacitor 5 is 10 volts. Resistor 1 and resistor 2 equal to 5 volts drop across them because of the equal values. The output is taken between the point A and B to find the output voltage algebraic added between the A and B, the loop AC or ADB, point A to B, point A to point D is negative 5 volts, point D to B is 5 positive 5 volts. The algebraic sum of these 0 volts and output voltage 0 resonant. The voltage on the branch ACB will figure to the same output with the found B because the circuit branch is parallel. Our current flow is parallel due to resonancy. When the input signal reverses the polarity, the signal voltage of the cuff, the inductor 2 is also reversed. The diodes will reverse by if no current will flow. Meanwhile, capacitor 5 most of it is charged because of the long time constant offered with the combination of resistor 1 and 2. The slow discharge helps maintain the output. Operation above resonancy. The tuned circuit that operates frequency higher resonancy of the tank conduct with the secondary circuit current lags the primary voltage. The secondary current secondary voltage 1 nearly favor the primary voltage. For the voltage 2 is shifted further out of favor of the primary voltage. Vector sum of the voltage 1 and voltage primary larger than voltage 2 and the voltage primary. Therefore, the voltage applied with the cathode diode 1 greater than the voltage applied with the anode diode 2 above resistance. Alright, assuming that the voltage developed above the resonance of the shift, the higher voltage of the cathode 1 and cover the capacitor 3, the charge of the 8 volt larger voltage the anode of the diode 2 with the capacitor 4, the charge of the voltage of the capacitor 5 remains sharp with the sum of the 2 volts to 10 volts. Again, adding the voltage of the ACB and A or ADB points A and B, you can find the output voltage. Point A to AD equals negative 2 volts. Point D to B shows 5 volts. The algebraic sum of the output of the 3 volts. For positive 3 volts will tune above the resonance during the negative half cycle. The input signal of the diodes are reversed by if the capacitor 5 helps maintain a constant output. Your operation below resonancy. When tuned circuit operates below resonancy figure is capacity. The secondary circuit is led by the primary voltage. The secondary voltage is nearly the phase of the primary voltage. The vector over the secondary voltage over the primary voltage is larger than the voltage 1 over the voltage primary over the voltage applied with the anode. The diode becomes greater than the voltage applied with the cathode at diode 1 below resonancy. Assuming that the voltage developed below resonancy, the higher voltage of the anode of the diode 2 with the capacitor 4 with the 8 volts, the lower voltage with the cathode capacitor diode 1 with the capacitor 3 charged with the 2 volts, the capacitor 5 remains charged into the sum of the 2 volts of the 10 volt with the output voltage equal to 8 volts plus 5 volts for the negative 3 volts tuned below resistance. During the negative half cycle of the input cycle, the diodes are reversed by if the capacitor 5 helps maintain the constant output. Alright, your advantage of the ratio detector. The ratio detector is not affected by amplitude variation of the frequency modulation wave. The output of the detector and adjust for the automatically average amplitude of the input signal with the capacitor 5 charges the sum of the voltage across the resistor 1 resistor group with the cover the time constant with the 10 filter out any of the noise and impulses before the capacitor 5. Sure the discharge higher or lower potential noise disappear. The difference in charge of the capacitor 5 is slowly not discernibly and the output of the ratio detector can be operated with as little as 100 millivolts and how much lower the required limiter saturation, less gain than the required of the preceding stages. Alright, your gated beam detector is frequency modulator, demodulator, employing with a complete limiting different detection gated beam detector. They are sometimes referred to the quadratic detector simplified diagram as a gated beam detector shown in figure 316. Gated beam tube detector simplified radio frequency modulator. The output voltage is 0 with the input frequency equal to the center frequency. The input frequency is above the center frequency. The output voltage goes positive when the input frequency drops below the center frequency. The output voltage goes negative. Circuit operation. The gated beam detector employed with a specifically designed gated beam detector limited to the tube is shown in figure 317. The focus of the electrode forms a shield around the tube of the cathode, except for the narrow edge slot with electron beam flows. The beam with electron flow toward the limiter grid, which acts like the gate. The gate is open. The electron beam flow through the next grid, which close the gate complodes stop the beam. Plate, quadratic grid, screen grid, limited grid, focused electrode, cathode. Alright, after the electron beam, after the limiter grid, the screen grid focus with the beam short with the quadratic grid. The quadratic grid acts as much for the limiter grid, either opens closed with the path of the electron. Two grids acts as the limiter end of the gate on the digital device. Both the gates must be open the path of the electron to the plate. Each grid can be cut off the plate current and the gate was presented in the module Neets module Introduction to Number System, Boolean, Algebra, and Logic Circuits. Look again at the circuit, figure 316. No signal applied with the limiter grid of the tube that conduct the electron beam moved in either the quadratic grid. They induce the current into the grid, which would develop the voltage curve of the high merit tanking circuit. Capacitor 3 charges until then becomes sufficient, then negative to be cut off the current for the flow of the inductor 3 tends to keep the current moving as it feels collapse. The discharge of capacitor 3. Capacitor 3 discharged sufficiently. Quadratic grid becomes positive. The grid current flow within the cycle repeats itself. The tank of the inductor 3 and the capacitor 3 are tuned current center frequencies have received a frequency modulated signal so that it will oscillate at the frequency. Waveform of the circuit is shown in figure 318. View A with the frequency modulated input signal with the limiter grid action with the center wave. The wave shape view because of the tube is either cut off or saturated. The view very quickly. The input wave, note the square wave, the current waveform is passing through the limiter grid. Saturation at 0 volts. The graded beam detector waveforms in limiter grid. Graded beam detected waveform. The quadratic grid voltage of the capacitor 3 lag with the current but due to the VUC, the result of the series pole with the shown view D appearing in the quadratic grid the center frequency, but lagging limiter grid voltage 9 degrees. Because the quadratic grid is the same conduction, the cutoff limits for the limiter grid resonant current waveform will be transformed to the square wave. Both limiter and quadratic grids both must be positive at the same time when they have the plate current and see how much conduction time occurs for each cycle of the input with overlaying the current waveforms view and B and D and view E. The times both grids are positive, shown with the shaded area of view E. These plates or current pulses are shown in operating resonance in view F. Or show you limiter grid, quadratic gate, overlay, B and D gate, beam detector, and resonant resonance. Now consider what happened to the deviation frequency of the input, the frequency input, and increase the frequency across the quadrant tank. Also increase the resonancy of the tank appear with the collapsed acid of the inductive current voltage. The tank applied with voltage more than 9 degrees, shown in the view G. You know the view H. The two grid signal have been moved more out of favor of the average plate current level that has decreased. Limiter quadratic grid gate beam detector resultant above the resonancy. As the input frequency decreases, the output action takes place with the two grid signals much more than the phase shown in view 1 of the average plate currency issue shown in view J. Limiter grid, quadratic grid, gated beam detector waveforms resonant below resonancy. View K show the resonant plate current pulse the frequency modulator signal is applied with the gate beam detector. The plate load of the resistor 4 capacitor 6 form the integration network of the filters. These pulses form the sine wave output. Figure 318 show the gated beam detector waveforms. Also, advantage of the gated beam detector. The primary advantage of the gated beam detector lies with extremely simplicity. It employs only one of the two, yet provides effective limiter. Limiter detection requires effectively few components, very easily adjusted. There are more than 3 types of the demodulator presented in this chapter. However, they are representative types which will working with the principle involved in these operations are similar to the other types. You will now briefly study phase modulation with the use of the same basic circuitry as the frequency modulator demodulators. And that there.